Today, we're going to mostly focus on semantics and Hoare logic. I'm just importing a bunch of libraries. You can also see these imports in the file on Canvas. So the first thing I did was that I wanted to define the concept of a state in a program, or the concept of evaluation, let's say. So I wanted to have a function that maps my variables to values. And this is what I mean when I say total map. So total map A is a type, and it's the type of functions that map strings to values of type A. So I'm just assuming that all of my variables are strings. And then I define the empty function, or the empty map, which basically maps everything to a default value. And then I define the notion of update is that I have some map M, but I want to update so that it maps the value of X to A. And remember, M is a function. So I'm just going to create a new function, and this is a lambda expression. It's a new function that takes X prime. And if X is equal to X prime, then it returns V. Otherwise, it just returns M of X prime. So just updating the valuation. And of course, in our program, we want to say that our states are total map of nats. So I'm assuming that all of my variables are going to take natural numbers. And so every state is just a mapping that takes the name of a variable and gives me the value of that variable. Okay, I defined some basic notation. Again, I'm not going to talk much about notation, just look at the COC manual for that. But basically, I use this notation to say that this is the map M, except that now X is being mapped to V. And I use this one to just say the map that consists only of X being mapped to V. And then we saw that we can define our arithmetic expressions in our while programming language. So all I'm doing here is trying to define my mini programming language while from the theoretical sessions in COC. First, I'm going to say that I'm defining my arithmetic expressions. And an arithmetic expression, by definition, to the grammar that we've seen before, can be either a number or a variable or the sum of two arithmetic expressions or some arithmetic expression A1 minus A2 or A1 times A2. And I have a constructor for each of those cases. So this is an inductive type definition which defines all possible arithmetic expressions. And then based on that, I also defined Boolean expressions. So I have true, false, equality, negation of equality, not, and all of these good things. Okay. And then I actually defined a ton of notation so that I don't have to write all of these names of constructors all the time. So all I need you to remember at this point is that whenever I do this kind of notation, so whenever I open an angle and bracket and then close the bracket and angle, anything that I write inside there is in the while programming language now. So I'm using this notation to distinguish between my COC code and the code that is in the while programming language, and I'm actually analyzing. I also defined 4 variables, W, X, Y, and Z. And we got to this point where I showed you that you can actually check the type of these expressions. So I can have something like this. And again, I'm setting the scope to be the scope of my while programming language. And then COC can easily check that this is, for example, an arithmetic expression. And then I defined denotational semantics for my arithmetic and Boolean expressions. So I defined functions that take the current state of the program and a particular arithmetic expression A, and then they evaluate A in the current state. And this was, again, very simple. I just said that if it's a number N, it's just that number. If it's a variable X, you just take the value of the variable. And for the other cases, you just do the operation. So if you have an expression A1 plus A2, you first evaluate A1, then evaluate A2, then take the sum. Okay. And the same thing for Boolean expressions. Basically, I have another function called beval, which evaluates a Boolean expression at a particular state. And of course, if I evaluate an arithmetic expression, I have to return a natural number. If I evaluate a Boolean expression at a state, I have to return a Boolean. Okay. Pretty nice. So now that we have our expressions, we can actually define the statements or the commands or the programs in our while language. And remember that when I was teaching you about the while language, this was the syntax that we wanted to have. So I want to have skip, I want to have assignment, sequential composition, if, and while. So now again, I define a command or a program as an inductive type. And I say it's either skip or it's an assignment, but if it's an assignment, it should take a variable x and an arithmetic expression a. So it's assigning a to x. Or it's just a sequential composition of two other commands, or it's an if, but if it's an if, it should have a guard, which is a Boolean expression, and then a then part and an else part. And these are C1 and C2, which are themselves programs or commands. And or it's a while. And for while, we should again have a guard, which is the condition of the while, and some body C, which is what's being run in every iteration. Okay, and then I again defined a lot of notation so that I don't have to write the names of these constructors. I can just write skip, I can write assignment like this, I can write sequential composition like this, and of course I have if and while. Okay, so one example we saw was that if I want to write a program in my while language that just computes the factorial of a number x, this is a program that does that. So it says set z to x and then start with y equal to 1. And as long as z is not 0, multiply y by z and decrease z. But very importantly, this notation means that this is a program in my while language and not part of my Coq code, okay? And if I print it, it actually tells you that the type of this whole program is command or com. And yeah, so here's an arithmetic expression. Its type is arithmetic expression. Here's a Boolean expression. The type is correct. Here's a command and the type is correct. And we saw some more examples of programs as well. Okay. Now, the program that we saw towards the end of the previous session was this one. So this is an infinite loop. In my while programming language, I can write programs that do not terminate. So in this case, I have while true do skip. It's an infinite loop. So this tells me that I cannot really define my denotational semantics as just a function in Coq that runs my Coq functions have to always terminate and return something, but I can have programs that don't terminate. So if I want to have something that looks like our denotational semantics and just, let's say, takes some state and some command, so runs this command on this initial state and returns the state after the command finishes, I can do this for all cases except for the case where I have a while. And we did this in the last session. So we said that if not change, if the command is an assignment, the state changes, but we can just update the map. And the way we update the map is that we were assigning a to x. So we first evaluate a at the current state. And then we update the state by setting the value of x to be the result of that evaluation. And then we had these things for sequential composition, if, and not for while. We don't know what to do for while here. That's impossible. Okay. And then we saw an example. So for example, if I have this initial state where z is 4 and x is 2, and I have this program, which first subtracts x from z and then increases x by 1, then I can say call the evaluation function on this initial state with this program. And it does, and it gives me a result. And the result is also a state. And a state was just a function that maps variables to their values. So I can ask what is result of z, and it says it's 2. And you can see that, of course, if I run this program on this initial state, z should be 2. And I can also ask for the result of x. Okay. So we saw that we cannot do much with denotational semantics or with function-based semantics. So instead, we said, let's do operational semantics. And actually, in the last session, we saw big step operational semantics. In this session, we're going to see small step operational semantics. So I defined this notation, ST, ST prime, which basically means big step operational semantics. So if I start my program at ST and my program is C, it will terminate at ST prime. That's what this means. Okay. So in operational semantics, we always write proof rules. And actually, let me find the slides for big step operational semantics so that I can show you that these are basically the same proof rules. These are the slides from our lecture on big step operational semantics. And these were the rules that we had. Okay, so these are first the rules for evaluation. I don't care about those. I care about the rules for big step semantics. So for big step semantics, we said that if our program is just skip, it just terminates. If our program is of this form, it's doing an assignment. We have this rule. So it's doing the assignment x equals to a, and it's assigning the value of c. The value of a at the current state is c. So we have this. And then we have these rules. We basically had rules for while, for if, for else, all of those nice cases. So let's go back to Coq and let's see how we are writing the same rules basically here. So this is an inductive proposition called C-eval. So it just defines some sort of relation, mathematically thinking about it. So what kind of relation is it? It's like a ternary relation. You have a command, an initial state, and a final state. And it's in this relation, if from this command, from this initial state, using this command, you can get to this final state. Okay? So I have several rules. I have a rule for skip. And coming back here, this is basically the rule for skip that we had here for this one. Okay. What does my skip rule say? It says for all states ST, from ST, if I run skip, I will end up at ST itself. Very simple. So this is just the same thing as we've seen in our theoretical lectures, except that we're writing it in a different notation in code. So the rule for assignment is that if I have an assignment which says assign A to X, and if I start at some particular state ST, I will get to the state which is obtained by updating the value of X to N in ST. And what is N? N is the result of evaluating this expression in the current state. Okay. And then we had a rule for sequential composition, which basically said that if starting at one state with C1, I get to this second state, and starting at that second state with C2, I get to this third state. Then starting at the first state and doing C1 followed by C2, I get to the third state. And the rest of these are basically the same. I have a big step rule for if in the case where the condition is true. I have another one in the case where the guard condition is false, and also for while. So maybe the only really interesting case is the rule for while when the condition is true. So I'm saying that if the condition B is true at the current point of the program, at the current state, okay, and if running C from the current state would get us to this other state, ST prime, then if from the current state I run while B do C, and if from that state ST prime I run the while, I get to a third state, ST double prime, then from the current state ST, if I run the while, I will also get to that third state ST double prime. So this is like unwinding or unrolling the loop for one iteration. Okay. Great. But let's do something new, actually. Let's do something that we haven't done before. let's define small step operational semantics. Okay, so to do a small step operational semantics, I'm going to go back to the slides that we had for a small step. Okay, again, we had a bunch of rules. Okay, so one rule was that if I start with skip and some value, I just end at that value. This was the rule for assignment. Okay, so if my program is simply just assigning A to X, it will immediately terminate, and it will terminate in the state where I've just updated the value of X. We had rules for sequential composition. Well, in our programming language that we just defined in Coq, we don't really have halt, so you can ignore the part about halt, but we have these rules. And of course, we had two rules for if, for the cases where it was true and false. So if it were true, I would just run the then part. So I would transition from having this program at the current state to having only the then part at the same state. And if the condition was false, I would only have the else part. So you see, this is a small step. This is one step of execution at a time. And then we had these rules for while, which basically said that if my condition is false, I just don't do anything. My while doesn't run at all because the condition of the while, the guard B, is false. But if the guard B is true at the current state, then I have to first run one iteration of my while loop. I have to run P, and then I have to run my while loop again. Okay? So let's see if we can define this here. I want you to actually write this on your own, so I'm going to give you some time to write this. Let's say I want to define an inductive relation, which basically just does one step of the execution. And what does it take? It takes the initial state and the initial program. And it also takes the final state and the final program. And it should tell me whether it's possible to go from that initial state and program to the final state and program. And again, remember, this is an inductive proposition. So you have to give me proof rules, just like the previous case. So just try to translate all of these rules that we had for small step semantics to Coq. And again, all of the rules for small step semantics are actually available on Canvas. You can look back at those and just try to write the rules one by one. Okay, let's do this. This is actually the answer, or at least one possible answer. It looks complicated, but it's not really complicated. Okay, so what do I have? I have an inductive proposition called one step. And what is my intuition? My intuition is that I should be able to get one step of, let's say, state program, state prime, program prime, if and only if running one step of the program P on the state ST leads to P prime on ST prime. Okay, this is my intuition. So I have to now give proof rules where the conclusion or the result of the proof rule is of this format. Tells me when I have the one step of STP, ST prime, P prime. Okay. So let's actually just take all the proof rules that we had for one step execution. Again, we'll go here to small step operational semantics. And let's just look at the simplest rule that we had. So our simplest rule was that if my program is skip and I'm running it on some state, now in the slides I'm calling it val, but actually in Coq I'm calling it ST. So val and ST are basically the same. If I have skip and I run it on ST, I will end up at the same state. But you see, that's problematic for me because of the type checking again, because I want to define this relation or this inductive proposition in a way that I always have this format, two states and two programs. right? So I just don't distinguish between skip and the empty program because I don't have a concept of the empty program here, okay? So instead, the rule that I write for skip, and I call it rskip, is going to be like this. I'm going to say that for every state st and every program p, remember that com was command or program. So for every state st and every program p, if I have a program that looks like this, skip followed by p. And remember, whenever I want to write programs in my while language, I have to change the scope. Otherwise, Coq might think that this is Coq, but this is in my while language. So I say if I start at this state and the program I have to run is skip followed by some other program p, then I can just remove this skip and I can say start just in one. You stay at the same state, but now you have to run the program p. Okay. And actually here I don't need this. I can just write it like that. Okay. So this is my first rule. But let's just go over how this rule should be read. So I'm saying I have a rule called rskip. What does this rule say? It says that for every state st and for every p, this thing holds. One step of st, skip p, st p. And this thing just says that, again, our intuition is that it means that running one step of this program on st keeps us at st, but now we have to run this program. Okay, so this is what my first rule says. And my skip rule is different from the skip rule in the theoretical lectures because I don't have a concept of an empty program here. And I'm just showing the empty program with skip itself. So instead, the rule that I have for skip is that if you have skip followed by something, you can remove the skip. Okay. Let's look at the rule for assignment. What was the rule for assignment? It said that if I'm at some state and I'm doing an assignment, I will terminate at the same state, except that the value of the variable that got assigned has to change to the actual value that that expression had in the current state. Okay. So again, I write a new rule. I call this rsassign. So forget about these parts and just focus on the part that I'm writing here. I'm saying, suppose that when I take the arithmetic expression a and I evaluate it at the current state, it evaluates to the value n. Okay. Then I can say that in one step, this step, and my program is to just assign x to a. Which state do I go to? I go to the same state, except that the value of x is now n, because remember, a evaluated to n in the current state. Okay, and what happens to my program? Now, this is the part where, again, things get a little bit weird. I don't have an empty program, so I have to put something for the empty program. I just put skip. Okay. Now,
P and then put P at the end, the same. And then put semicolon after X, assign to A, and then put semicolon to the P to replace.
Yes, but that's not the rule that we had here. So the rule that we had here was if my program is just this assignment, what happens? So here I said what happens is that I will have the empty program at this state, but here I'm just using skip instead of the empty. Yeah, but the rule you say is also correct. It's just not the same rule. Yeah. Okay. What is the rule that I have for sequential composition? Saying that if I start at program P and valuation val, and in one step I go to P prime val prime, then if I do from PQ with valuation val, I will go to P prime Q and valuation val prime. Okay. So basically it's the idea that if you have a sequential composition of P and Q and you want to run one step, you have to just run one step of P. So what does this rule say? It says that for all states ST and ST prime and all programs P, P prime and Q, if running one step of P at this state gets me to P prime at this state, ST prime, then running one step of P followed by Q at the same initial state gets me to the same state ST prime, except that now I have to prime followed by Q from that point onwards, okay? So it's literally this rule, except that we don't have halt in our programming language right now, so I don't have this part of it. Okay, nice. Next rule. So what happens if I have an if and the if condition holds? So the rule for if, you see, if the if condition actually holds, in one step, I don't change my but I just say, instead of running the whole if, I just have to run what was in the then part. So I want to write this rule in Coq, and I call the rule R if true. So this is the name of the rule again. And again, this is universal quantification. So it says for every state ST, for every B that is a Boolean expression, and for every P and Q that are programs, we have this, okay? So this is now the actual core of my rule. What is the core of my rule? It says that if I evaluate B at the state ST and it evaluates to true, then I know that running one step of this program, and look, I'm changing the context here, and I'm going into my while language. So everything in here is in the while language. So running one step of the program, if B, then P, else Q, from the state ST, is going to take me to the same state ST, but now I have to run the program P. Okay, and this is because B at ST evaluated to true. Okay, now I need another rule for the case where I'm doing if and the condition is actually false. So this rule is exactly the same, except that instead of running P at the end, I have to run Q at the end. So it's literally the same rule as the one above, except that it says if B evaluates to false at the current state ST, then running one step of this program from ST keeps me at the same state ST, except that now I have to run Q. I have to run the then part. Okay. By the way, I just put this file, the Hoare.v, also on Canvas, so you can just download it. You don't have to write this. Okay. Now we get to the rules for while. Again, this is the most complicated part, but it's not that complicated at this point because you already know how to translate from the notation of rules to the notation of rules in Coq.
Copy for previous function.
Yes. So I have a rule for the case where my while guard is actually true. So I say that if B at the current state evaluates to true, then in one step, what happens if I run one step of the while? Well, I basically stay at the same valuation as T, but now I have to first run P. I have to run the body of the while loop, followed by the while loop again. Okay, great. And the next case and the last case is actually quite easy. If I have a while and the condition of the while is satisfied. So I have this program, while B do P, but when I evaluate B at the current state, it evaluates to false. Okay, so in this case, in one step, my program just terminates. So I end at the current state and I have no program to run, but we said I don't have a concept of empty program, so I just put skip instead. Okay, is this clear to everyone? Do you all understand what I'm doing here? Okay. Great. So now I finally have the concept of small step semantics. But if you remember, we also talked about the transitive closure of our small step semantics, right? So basically, what I'm defining here is that if I start at this state and program, in one step, I can go to this other state and this other program. But what if I want to define multi-step execution? I can just define another function, or actually to be more specific, I can define another inductive proposition. And I call this one multi-step. Now, what does this one mean? Intuitively, I want to say that given a state and a program and another state and another program, multi-step holds. So multi-step of ST, C, ST prime, C prime holds. If starting from the state ST and running several steps of the program C, I can eventually reach the state ST prime and the remaining program be C prime. Okay? So anyway, this is just the transitive closure of the previous relation. And in the past session, we've seen how we can define transitive closures in general, but I'm just going to define the transitive closure here. So I have two rules. I have a base rule, which says that if in one step I can go from P to P prime, if in one step I can go from STP to ST prime P prime, so I need both my state of variables and the remaining program that I have to run. If I can do that, then I can also do it in multi-steps. So that's the first rule. And the second rule is that if in one step I can go from STP to ST prime P prime, and then with multiple steps I can go from ST prime P prime to ST double prime P double prime, then in multiple steps I can go from the original state and program to the final state and program. Okay, so this is the definition of multi-step. Tell me the problem with this definition. What's wrong here?
Zero steps.
Yes, it doesn't consider the case where you reach in 0 steps. So it's only considering the cases where you reach in 1 or more steps. If you want to have the case with 0 steps, you have to either change your R base rule, or you can just add another rule. You can call this R0. And what this says is that for every state ST and every program P, I have multi-step reachability from STP to itself, to STP. Okay, if I add this, now it's correct. And actually, if I add this, then I don't need the next rule, because it's actually easy to get the next rule by combination, the second rule by combination of the first and third rules. Okay. Again, I define some notation because I don't like to write multi-step and one step. So I define it like this. I say, if I write something like this, STC, and then I put this kind of arrow, so 2 tildes and an arrowhead, then this means multi-step. If I put only 1 tilde, I mean 1 step. Okay, so this is just my notation. Now I have a theorem, and this is a theorem that is actually very easy to prove, but at the same time, very time consuming. So I'm not going to prove it, but I'm going to put it in your homework too. And this is the theorem. It says that basically our 2 types of operational semantics are equivalent. Remember, so when I was talking about big step and small step, I said that you will have the big step if and only if you can repeat the small steps and get to the same place, right? So this is the theorem that I want you to prove in your homework too. It says for any 2 states ST and ST prime and any program P, if my big step semantics says that running the program P from ST terminates in ST prime, then my small step semantics says that from STP, I can go to ST prime skip. Because remember, I showed the empty program with skip. And vice versa. And also, if I can go from STP to ST prime skip, using my my small step semantics, then using my big step semantics, I also terminate in the same place. Is the theorem clear to you?
Main idea is easy to.
Yes, the main idea is actually very much similar to the proof that we gave in the previous session that, well, actually I didn't give it, I just went over it, that denotational and operational semantics are equivalent. So it's a casework, but now you know how to use tacticals, so you should be able to avoid most of the casework very easily by just putting together some semicolons and tries. Okay. Nice. Now we want to go to Hoare logic later on, but before I can do that, I need to define replacement. Oh, actually, one more point that I forgot. Look at this thing here. In this rule, I'm saying this thing and this thing together imply this third thing. So instead of the and here, I can also put an implication. Okay, and this is a logical idea. The idea is that basically in propositional logic, A and B implies C is the same thing as A implies B implies C. Okay, and since these two are equivalent, in Coq, we usually prefer this kind of notation. So I write it like that, even though for humans, it's more intuitive to write it like this. Now, why do I write it like this in Coq? Because, well, imagine that I want to use this RTran in a proof. So this is a proof rule. This is kind of like an axiom that I can use in any proof, okay? So if I have this RTran, I would prefer to be able to just do intros and get everything up into the context, okay? So, and this ensures that, whereas if I have and, I have to do split or destruct, I don't want to do that. Okay. This is the theorem you should prove. Okay. Now, this is a function that I want you to complete. So this is a replacement function. What do I mean? I mean that I give you some arithmetic expression A, and I give you a variable X, and I also give you another arithmetic expression E. Now, what I want you to do is to go through the first arithmetic expression, and whenever you see X, replace it with E. Okay, so it's replacement of a variable with an expression inside another expression. And of course, the result of the replacement would itself be an arithmetic expression. So I want you to write this function now. We're going to go back and look at the definition of arithmetic expressions. It was at the very beginning, somewhere here. Yes. So we said that an arithmetic expression is either a number or a variable, or it's constructed using plus, minus, or multiply. Okay. So let's just do the replacement in each of these cases. So I just do a pattern match on my original arithmetic expression A. And I say, if it's just a number, well, return A. There is nothing to replace. I just want to replace the variable X with E. If it's a number, there is no X, right? If it's a variable X prime, you have to actually check. You have to check if this variable is the same as X, right? So if X and X prime are the same, then I should return E, because I want to replace the variable X with E. Otherwise, I just return X prime itself. Okay. The other case is that my main expression is of the form A1 plus A2. So it has two sub-expressions, A1 and A2. Well, here it's again very easy. I would first replace all instances of X with E in A1, and let's call that A1 prime. So let A1 prime be the result of replacing all instances of X with E in A1. I'm recursively calling the same function. And let A2 prime be the same thing just for A2. So I'm first doing the replacements in A1, then I'm doing the replacements in A2. And then I'm saying create this expression, create the expression A1 prime plus A2 prime. Okay. And it's the same for minus and times. So if it's A1 minus A2, again, I first do the replacement in A1, then I do the replacement in A2, and then I create this expression which uses the minus of the replaced versions. And here it's the same. If it's A1 times A2, I first replace in A1, then I replace in A2, then I take the times of the results. The thing that really makes this kind of hard to write is that you have to be very careful what's in which scope. So you have to be careful where to open this kind of braces and when to close them. Okay, nice. So now I want you to write the same thing, the exact same function, replacement, except that instead of replacing a variable in an arithmetic expression, I want to replace it in a Boolean expression. So I have a Boolean expression A, I have a variable X, and I have an arithmetic expression E. And I want to get another Boolean expression which is equal to the result of replacing all instances of X in A with E. So please complete this function. It should be very similar to the previous one. Yeah, and for the cases, you can just copy from the constructor from the definition of BEXP, right? You have all the constructors there, so you can just copy that and use that for the cases of your match. Okay, let's see this. Again, the idea is exactly as before. Yeah, we have many cases now. It's just that I have I have a Boolean expression a variable X, and an arithmetic expression E. And I want to replace all instances of X with E. So I just do a match on A, and I say, well, if my original expression is true, the replacement is not going to change anything, I'm going to get true. If my original statement is false, I'm going to get false. If my original expression is of the form A1 equals A2, I have to replace all instances of X in A1 with E. So that's what I do here. And I call the result A1 prime. I have to also replace all instances of X in A2 with E. And I do that and I call that A2 prime. And then instead of A1 equals A2, I will have A1 prime equals A2 prime. And it's exactly the same thing for not equal, for less than equal, greater. So these cases are exactly the same as before. This is actually a little bit interesting. So if my original Boolean expression is of the form not B1, okay? So I have to replace X with E in B1. But this is a replacement in a Boolean expression. So I'm recursively calling the same function. Whereas in the previous cases, I was calling the previous function that I had for arithmetic expressions. Okay. But yeah, other than that, other than the fact that I'm recursively calling the same function, the idea is exactly the same. So I'm doing the replacement in B1, and then I'm saying take the negation of the replacement. Because the original expression was the negation of B1. And the same thing for AND. So if I have B1 and B2, I first replace X with E in B1, call that B1 prime, then replace X with E in B2, call that B2 prime, and both of these were again recursive calls to the same function. And finally, instead of B1 and B2, I will have B1 prime and B2 prime. Okay, welcome to the last session of this course. Some of you are happy because you no longer have to do Coq, but you have to do the second homework still. So don't be too happy about the course ending. Okay, we're finally at a point where we can define Hoare logic and the proof rules of Hoare. But before that, I just want you to remember that in Hoare logic, we had this particular type of item, which is a Hoare triple. So we had Hoare triples of the form A, P, B, and the idea was that A is the precondition, P is the program, and B is the post condition. But one other thing that we needed, especially for the last rule, for the rule of consequence, where is the consequence rule? Okay, here. So we need to also define when a particular Boolean expression, another Boolean expression, because we need that in order to define our consequence rules. So first, let's define that, and then we'll come back and define our Hoare triples. This is actually the simplest definition yet. So let's say I have two Boolean expressions, A and B. When can I say that A entails B? Okay. When is B a consequence of A? Well, if for every possible valuation to the variables, if A evaluates to true, then B also evaluates to true, right? So the idea is that A entails B if A entails B on every possible valuation or on every possible state. So I just define this. So I define entailment. And then I also give it a notation. Again, another type of arrow again. You have to now make sure you understand the difference between all of our arrows. So this is an arrow with a dot in between. And I'm using this for the entailment between Boolean expressions, between A and B of type Bexp. Okay, now I'm ready to define my Hoare triples. Okay, so again, a Hoare triple consists of two assertions, and these assertions are going to be Boolean expressions for us, and a program in between. And program is the type com in our current setting. We've seen some examples. We will come back to these examples. But very importantly, I just had a bunch of axioms. So if I want to define Hoare logic, I just have to define these axioms. Okay. So here's what I'm going to do. I'm going to define an inductive proposition called Hoare. And the idea is that Hoare of A, P, B holds if I have this, if I have A, P, B. Okay. That's what I want to do. Okay. So now I have to, again, give proof rules. I have to say how you can prove Hoare of A, P, B. And if you look here, Hoare is, again, an inductive proposition. It takes a Boolean expression. This is my A. It takes a command or program. This is my P. And it also takes another Boolean expression, and this is my B. Okay. So first, let's look at the rule for skip, the axiom for skip. The axiom was just this. We didn't need any assumptions. A, skip A always holds. So if I want to write it here, I have to say for every A that is a Boolean expression, I can have Hoare of A, skip A. Okay, easy. Now let's look at assignments. So this was the thing that was a little bit non-trivial at the beginning when I was teaching you about Hoare logic. So if my program assigns the expression E to the variable X, and if I want to have A in the post condition, I should have A in the precondition, except that every instance of X should be replaced by the value of E. And we did examples of this. And the example was that if I have, for example, X equals X plus 2, and at the end I want to have X less than N, at the beginning I should have X plus 2 less than N. So I just take my post condition and I replace X with X plus 2, and that's what I can put in the precondition. Okay, but anyway, this is my rule or my axiom schema. I'm going to write it here as a rule H assign. So I'm going to say for every Boolean expression A, variable X, and arithmetic expression E, I have this. If I have this Hoare triple, and in my Hoare triple, the program is just a program that assigns E to X, and let's say that my post condition is A. Then my precondition should be A, except that every instance of X is replaced with E. And that's why I wanted you to write the replace function, because I needed it here. Okay, and then this Hoare triple holds. This is the entire Hoare triple. Okay. Let's go to sequential composition. This was actually the easiest kind of axiom that we had. So it says that if APC and CQB holds, then APQB holds as well. So I run P starting from precondition A, and I ensure postcondition C. From there, I run Q, and that ensures postcondition B. So of course, if from A I run P followed by Q, I will reach B. Okay. So I'm not going to spend too much time explaining Hoare logic. I'm just focus on how to do it in Quark. Okay. So this is the rule for sequential composition. I say for every A, B, and C that are Boolean expressions and every P and Q that are programs or commands, if I have the Hoare triple APC, and if I also have the Hoare triple CQB, then I have the Hoare triple A, the program is now P followed by Q, and then the postcondition is P. Okay. Now let's go to if. This was the rule that we had for if. So I need two assumptions here. So B is the guard of the if here. And I have to say that if A and B holds and I run P, then big B will hold. And if A and not B holds and I run Q, the else part, then again big B holds. And from this, I can say I get this Hoare triple. Now I'm going to write it here, H if. I'm going to use B for B, and for small b, I'm going to just use G as the guard of the if. So again, I'm saying suppose that I have A, G, and B, which are Boolean expressions, and P and Q, which are commands or programs. And let's say that this is the Hoare triple that I want to achieve. I want to find, I want to somehow prove the Hoare triple that says, my program is this, if B, then P else Q, my precondition is A and my postcondition is B. So what do I need for that? I need to say that if A and G holds, okay, oops, I have to put G here, yes. If A and G holds and I run P, then I should get B, so I need this Hoare triple. And I also need this Hoare triple. If A and not G, and then I run Q, then I will get B, okay? And again, instead of putting an and here, I'm just putting implication because I told you that these are the same in these cases. So this is the case for if. Nice. Now, let's write the rules of consequence. Actually, I'm going to just write one rule of consequence, and this is the most general case, so this last one. So we've seen that if A prime entails A and B prime entails B, and I have the Hoare triple A, P, B, then I also have the Hoare triple A prime, P, B prime, okay? So this is strengthening the precondition and weakening the postcondition. So now if I want to write it here, I give it a name. I say this is H consequence. And here's what I say. I say if A prime entails A, exactly this, and B prime entails B, and I have the Hoare triple APB. So you see, this is exactly this rule. Then I have the Hoare triple A prime PB prime. Okay. Finally, the rule for while. Remember that for while we actually had to also add an invariant A. Okay. So the idea was that if A is a loop invariant, and then I have this Hoare triple that says if I have A and B and I just run the body of the loop once, then I'm guaranteed to have A at the end of it. So A remains there. Then I also have this Hoare triple, which says A while B do P. And then at the end, as the post condition, I have not B because, of course, I should have not B because that's the only way that the while ends. And I also have A because A is preserved in every iteration. So let's write this rule. Again, exactly the same as before. I say my program is while b do p. And I say if I have this Hoare triple, which is a and b, p, a. Then I also have this Hoare triple, which is a while b do p. And on this side, I have as post condition not b and a. Okay, that's it. That's the definition that gives us all of Hoare's rules, basically. Nice. Now we have Hoare logic. First of all, let me just define some notation. I actually write my Hoare triples like this. I don't want to use curly braces here because we have too many curly braces in our notation already. And anyway, our notation is already really hard to read. But anyway, this is how I'm going to show a Hoare triple. So I define this notation. Here's the first theorem that I want you to prove. So this is a Hoare triple, and the Hoare triple says that precondition is true. The program is just a very simple program that assigns 12 to x. And I want you to prove the post condition x equals 12. Yeah, it looks trivial, but it's not trivial at all.
I don't know how to start with.
Yeah, so try writing a proof using pen and paper, and then try to translate every step of your proof for Coq. So this is what we want to prove, and this is a Hoare triple. It's a Hoare triple where the precondition is true, the program is just one line assigning 12 to x, and the post condition is x equals 12.
It's so trivial. Assign to 12, then x must equal to 12.
Yes, it looks very trivial, but
how to extract this statement in code?
Yeah, exactly. So which rule do you want to apply? Yes. Normally, I would want to apply the rule for assignment because, of course, my program is just a simple assignment. Now, what is the rule for assignment? Let's look at it. It's H assign. And it looks like this. It says you have the Hoare triple, which looks like this. So the precondition should be replace in A, X with E. The program should just be some assignment to X, right? And the post condition should be A. Now, what happens if I just say apply H assign? Yeah. So there is a problem here. What's the problem? Let's look at H assign. So if I want to apply it to this goal, Coq can understand that, well, A is the third part, so it's this one, right? And it can also understand that the program should be this, x equals 12. So here, it understands these parts. It understands that the expression E should be 12 in order for these two things to match. But then it has to also match the left-hand side with this expression, with replace AXE. But the left-hand side of this particular Hoare triple is just true. So it says, I don't know how to match true with that. I don't know how to unify true with that expression. Okay. So this shows us that we have to actually make sure that instead of having true here, we have exactly this expression. We have replace of A is this post condition, and X and E. I have to create all of that before I can apply H assign. Okay. So how can I do that? Well, I can apply H consequence, right? So let's say that I want to apply H consequence. What do I have in my H consequence? This is what I have in H consequence. I have A prime A, B, B prime, blah, blah. And at the end, I get a Hoare of A prime, P, B prime. So let's say I want to apply it. I say apply H consequence. Now, here's what it says. It says that, well, H consequence gives the Hoare triple A prime P B prime. And I have that here as my goal. So Cook says, I know what I should put for A prime, P, and B prime, because I have it in my goal. But I don't know what I should put for A and B. Right? Because there is no context that tells Cook what to put for A and B. Okay. So in this case, I actually don't want to change my post condition at all. So I say apply H consequence with, and then my B is just going to be the same post condition, x equals 12. But what do I want as my precondition? I want something that lets me easily apply H assign. And that thing is this, replacement in this expression of x with 12. Right? Does that make sense? Are you all happy with this? So I apply this H consequence with these particular values of A and B. And you see, this is generally always the hardest part of automating Hoare logic. So you can automate almost everything in Hoare logic, but when it comes to the consequence rule, there are infinitely many ways of applying it. You can have many different things for A and B. And there is no way that a machine can just figure out what to put there. And the same thing happens when you're applying the while loop. You don't know what the invariant should be. You need a human who actually reasons about it and gives the invariant. Okay. I said apply this H consequence. It says, okay, so you have to prove two implications. You have to prove two entailments. Because in H consequence, you have to prove that A prime entails A and B entails B prime. So these are now my two goals. Okay, my first goal is to prove that true entails this. Okay, and what is this? This is just x equals to 12, but you're putting 12 in place of x, so this is basically 12 equals 12. So I say simplify, and it gives me exactly that. It says true implies 12 equals 12. Okay, now I just say compute. Okay. So it computes both sides. And now I do intros, and now I just have to prove true is equal to true, reflexivity. That's it. The next one is also kind of obvious. It says that you have to prove that x equals 12 implies x equals 12. Oh, yeah, this is basically our post condition. We didn't change the post condition, but anyway, we have to prove that it entails itself, right? So here I just say, let's unfold the definition of this arrow. And remember that the name of this arrow was actually entails. So the arrow is just notation for entails. So I say unfold entails. So this is actually what I have to prove. I do intros. And now, as you see, I have the assumption and the goal that are basically the same. So I just say assumption. Okay. Now, based on this, after applying the H consequence rule, I have to prove this Hoare triple. But this Hoare triple looks much better. This is exactly what I can give to H assign. Because look at this Hoare triple. So this is my program, and my program is assigning 12 to X, right? And on the right-hand side, I just have some post condition, in this case, X equals 12. On the left-hand side, I'm saying the same post condition, except that you replace X with 12 in it. So this is exactly the case where I can just apply the rule for assignment, and I can say apply H assign. Yeah. So you see, your intuition was correct. We have to apply H assign, but in order to apply it, we have to make sure that whatever we have syntactically matches H assign. And in order to do that, we have to work with H consequence. Okay, next theorem. Prove this one. Prove this Hoare triple. So our precondition is y is greater than 0. Our program is quite easy. It just assigns y to x. And our post condition is that x is greater than 0 and y is also greater than 0. Okay, let's see this. And then I'm going to give you another thing to prove. Okay, this is the thing that we want to prove. This is the Hoare triple. So our precondition is that y is greater than 0 our program just assigns y to x, and our post condition is that both x and y are greater than 0. Again, ideally, I want to apply hassign. But before I apply hassign, on my left-hand side, I should have the replacement of right-hand side where I've put y instead of x. But what is that replacement? It's basically y greater than 0 and y greater than 0. So I want to put y greater than 0 and y greater than 0 here. So in other words, I want to prove that my current precondition, which is just y greater than 0, entails this precondition, y greater than 0 and y greater than 0. So it's just repeating it, right? But I have to prove that this entailment actually works. So I assert this, and now I want to prove it. So I say first, let's unfold the definition of the entailment. I do it, so this is what I have to prove. I do intros. Okay. Let's see what assumption I have. The assumption that I have is that y greater than 0 at the current state evaluated to true. And I want to say that y greater than 0 and y greater than 0 also evaluates to true. Okay, so it seems obvious that, well, if I evaluate 0, I should get 0. Do you agree with that? So let me just prove this super fast because I want to use it. So I say that the evaluation of 0 at the current state is 0, and that's just compute it and do reflexivity. That's it. Now I have it in my assumptions. Okay, now I say let's do an unfold on B eval. So let's see what my goal actually means if I unfold the definition of B eval. And I do it, and this is what my goal means. I'm going to unfold this B eval. So now this is what I have to prove. Okay, what is this? This is the evaluation of y. This is the evaluation of 0. But I already said that the evaluation of 0 is 0. But before that, I'm going to do the same unfolding here in my assumption as well. So I'm going to unfold B eval in H as well. Okay. What does this show you? It says that this entire thing is true. Right? But what do I have down here? I have that thing ANDed with itself. So I can just do a rewrite using H, and I get true and true. Yeah. Actually, I didn't even need my assertion at this point, but okay. So now true and true is of course true. I can do compute and reflexivity, or I could just do reflexivity. So that part is done. Okay, so I'm back where I was, except that now I have a new nice hypothesis that says that this one entails this one. Again, this is very trivial for us as humans. It's not trivial for Koch. Okay, this is the Hoare triple that I want to prove. Now, what do I want to do? I want to apply the consequence rule, and I want to basically replace the precondition with this larger precondition, which is like just repeating the precondition twice. So as usual, if I just say apply H consequence, it gives me an error because it says I don't know how to change the precondition and postcondition. So A is the precondition, B is the postcondition, right? So I have to tell it. I want to say that apply H consequence and change the precondition to this: y is greater than 0 and y is greater than 0. So just repeat it twice. How about my post condition? My post condition remains the same. So I just have to say, use the same post condition that I have for B. Okay, I apply this. Nice. Okay, so now I have to prove the prerequisites of H consequence. The first one is that I have to show that the old precondition implies the new precondition, but I had already asserted and proved that. So I just say it's an assumption at this point, right? Now I have to also prove this, but this is again a very trivial entailment. It's for my post conditions, but I didn't change my post condition. So it's just that the post condition entails itself. So I just unfold the definition of entails, do intros, and now my assumption and my goal are the same. So I just say assumption.
Oh, You can use,
Okay.
you can,
All of this was so that I can just, instead of having y greater than 0, I can just have it twice here.
we can do replace now.
Yes. So what's my goal? My goal is to apply HAssign, the rule for assignment. But in order to apply the rule for assignment, in my precondition, I should have this. Where is the rule for assignment? I should have replace of the post condition xe. So I take the post condition, replace x with, in this case, y. Okay. So I have to again do another assertion saying that if in my post condition I replace x with y, I get my precondition.
Oh, we cannot directly apply.
Yeah, we cannot directly apply that. So I assert this. I assert that if in my post condition I replace x with y, so the replacement of post condition xy is equal to the precondition that I have here. Okay. Now this part is easy because you just have to use the definition of replace, just do the replacement. So you can just compute it and then the two sides would be the same. Or in this case, I'm just going to say reflexivity. Okay, now that I have this assumption, I can rewrite my goal using this assumption. So I can say rewrite using H0. Finally, now my goal looks like the format that I wanted. Now I can apply the rule for HAssign. Because now I have an assignment x equals y in my program. I have a post condition x is greater than 0 and y is greater than 0. And my precondition is just the result of replacing the left-hand side with the right-hand side in the post condition. So now I can say apply HAssign. And this is it, QT. Okay. I want you to prove another theorem. This is the next theorem that I want you to prove. Oh, wait, I have two dots there. Okay, I want you to prove, again, this very simple Hoare triple, which is very clear to humans, but not to Coq. So my program just increases x by 10. My precondition, my assumption at the beginning of the program is that x was greater than 2. And at the end of the program, I want to just know that x is greater than 0. So my post condition is x is greater than 0. So prove this. And by the way, if you need some lemmas about natural numbers, feel free to add lemmas about natural numbers and just say admitted without actually proving the lemmas about natural numbers. Okay? But prove this. Prove this, and you can also add lemmas for natural numbers. Okay, so let me show you the proof because I want to then focus on another one that is a bit more interesting. I'm going to need a bunch of lemmas first, and I said you can just define whatever lemmas you want about natural numbers. We already know how to prove these things, and actually most of them are in Pressburger arithmetic anyway, so Leah would solve them, right? Okay, so I define a bunch of trivial lemmas. I don't give proofs for them, but in your homework, you have to give proofs for everything, okay? So the first one is that if n is a natural number, it's either less than or equal to 1 or greater than 1. Okay. The second one is that if n and m are natural numbers, n less than equal question mark m is true if and only if n is less than or equal to m. Again, this is a proposition, this is a Boolean, so it's just doing that. Yes. The other one is that if I have 3 natural numbers n, m, and p, and if n is greater than m, then n plus p cannot be less than or equal to m plus p. So this whole thing as a Boolean is false. Okay. Lemma 4, if n is a natural number, and if n is not less than or equal to 11, then n is not less than or equal to 0. Again, trivial, you can prove it later, but these are all the lemmas that I needed. So let's get to our theorem. So I want to prove this Hoare triple. So if in the precondition I have x greater than 1, and my program just increases x by 10, in the post condition I will have x greater than 0. So what do I want to do here? of course, ideally, I want to just massage this so that I can, in the end, apply the rule for assignment. Right. But in order to apply the rule with for assignment, I have to actually make sure that whatever I have on my left-hand side is the result of my post condition in which x is replaced by x plus 10. So I would ideally like to turn my post condition into this, into x greater than 11 instead of just greater than 0, right? And then I want to rewrite my precondition. Instead of x greater than 1, I want to write it as x plus 10 is greater than 11. Okay. Why do I want to do this? Because if I have this, then my precondition would be the result of replacing x with x plus 10 in the post condition. So all of this is so that I can apply the rule for assignment in the end. Okay. So I apply this H consequence, I apply the H consequence rule, and I say I want to rewrite my precondition like this, and I want to rewrite my post condition like this. Okay. So it says you have to prove a bunch of things. I'm going to do a casework here. So this one is about the precondition. So my precondition was x is greater than 1. I want to change it to x plus 10 is greater than 11. So it wants me to prove that x greater than 1 implies that x plus 10 is greater than 11. Okay, how do I prove this? Well, I first unfold the definition of entailment. I do intros. So here's a technique that would actually help you write some of the things easier. Sometimes you want to give a name to a particular expression, right? So here, what do I know? I know that I have a state, and I know that the variable x has some value in this state, and that's basically stx, right? And I want to do a casework. I want to say that, well, this value is either less than or equal to 1, or it's greater than 1. But in order to do that, I need to have it as a variable. So I just say, remember this expression as n. So this is basically saying I'm defining n to be equal to st of x. I could do all of this without doing this, without even defining n, but my life would be harder, so I prefer to do it. Okay, now I just do an assertion. I say n is either less than or equal to 1, or it's greater than 1, and this is the lemma that I had already put up there, not really proven, but you can prove it easily. Okay, so now I say, let's do a casework. Either n is less than or equal to 1, or n is greater than 1. So I say destruct h0. Let's do a casework. Okay, first case, n is less than or equal to 1. Okay, I want to actually apply my second lemma to h0. Now you see why I do this. So let's see what happens when I do it. You see, this was just a proposition. I wanted the Boolean form, because I need the Boolean form for the rest of this. And that's the role of lemma 2. It just writes it like this. So instead of having n less than or equal to 1, I get that n less than equal question mark 1 is true. Okay, now let's unfold some of our definitions. Let's unfold the definition of Boolean evaluation in this assumption H. And I get this. I say, let's unfold the definition of arithmetic evaluation as well. And this is what I get. So you see, I'm now completely done with arithmetic and Boolean evaluations. And this is just the value of x in my current state. Okay. Yes, but I already gave it the name n. So I do this, I replace it with n. So now you can see the contradiction. The contradiction is that I have something that is true and its negation is also true. And that cannot be. So I just do a rewrite. I rewrite h0 in h, and I get that the negation of true is true, but that's impossible. So I just do discriminate in h, and that's it. All of this was in my precondition, and for the case that n is 0. Now I'm still in my precondition, and I have to consider the case where n is greater than 1. Sorry, for the case that n was less than or equal to 1, now I have to do n greater than 1. So I do the same things as before. I unfold these definitions of b eval and then a eval. Okay,
We can rewrite that.
Yes, I can rewrite using this. So instead of having st of x, I can just have n. This is simpler. Nice. Now, here's an assertion that I want to make, which is quite funny. I want to assert, so I know that n is greater than 1. I want to assert that n plus 10 cannot be less than or equal to 1 plus 10. Okay, so I assert this. This is my third lemma from here, that if n is greater than m, you add p to both of them, the order cannot change. Yeah, so I apply that lemma, and now I get n greater than 1 on both sides, so this is assumption. Okay, great. Now, this is what I want to prove. I want to prove that the Boolean negation of n plus 10 less than or equal to 11 is true. But I know that this thing is actually the same as this thing, and I have the assumption that that's false. I have to do some simplify. So I do simplify in H1 so that I get 11 instead of 1 plus 10. And then I do rewrite using H1 so that I get that negation of false is true. And of course, at that point, it's reflexivity. Okay, everything I did until this point was to just show that I can replace the precondition, right? Now I have to show that I can do the replacement that I claim on the post condition. Okay, this is what I have to do. I have to show that x greater than 11 entails x greater than 0. Because remember, my post condition was x greater than 0. I wanted to replace it with x greater than 11. Okay, same thing. I unfold, I do intros, I unfold the definition of B val, both in the assumptions and in the goal. I do some simplification. And here's the thing. Look at what I have at this point. So in my assumptions, it says it is not the case that st of x is less than or equal to 11. And so what does that mean? That's like the value of x at the current state is more than 11. So of course, it's also more than 0, which is what the other one says. So again, I had a lemma for this because this is again with natural numbers. It's just saying that a number that is greater than 11 is also greater than 0. I apply that lemma, and this is an assumption. Okay. Finally, we have now rewritten our Hoare triple, and now our Hoare triple looks like this. This is much better, right? Hopefully you agree that this is better, because yeah, it seems like I can just apply the assignment rule, but again, I cannot, because in order to apply the assignment rule, here I should have the replace of post condition in which this variable is replaced with this expression. So I just assert that. I assert that if I take my post condition and I replace x with x plus 10 in the post condition, this is the post condition, I want to replace x with x plus 10. I get the precondition. I assert this. Okay. Now, asserting this and proving it is quite easy because, again, just compute it. And you see that they're the same on both sides, so reflexivity. Great. Yeah, now that I have this, I can rewrite. And now I finally have something that looks like the pattern that the rule for assignment actually accepts, right? So I have a post condition, and I have a precondition, which is the result of replacing x with x plus 10 in this post condition. So now I can apply HSI, and that's it, QET. So as you see, when you're doing these kinds of proofs in Coq, it's basically like doing it on pen and paper. The only really hard part is when you have to work with the rule of consequence, and you have to prove that like both sides of the consequence are correct. I've put some other examples here. We don't have time, of course, to go through this, but let's just talk a little bit about why they work and how we can prove them. So I'm not going to give you the complete proof. Look at this Hoare triple. It says that my precondition is that z is greater than 1 and less than or equal to 4. And then I don't touch z at all. I just say x is y times y. And then in my post condition, I have something trivial. I have x times x equals x times x.
Oh,
Okay, how would you prove something like this?
replace x and x equal to x and with true.
Yeah, so we want to replace this one with true. What do we want to do with this one?
We also, we have to replace the true with x equal to 1.
No, we want to replace this one with true as well. So basically, if we want to replace both of them with true and apply the rule of consequence, right? But then we have to show two consequences. And again, it's a proof like the previous cases. How about this one? So I want to say my precondition is that x times x is greater than 0. And then I set, sorry, the x times x is less than 0. So my precondition is impossible. And then my program just sets x to 1. And my post condition is that x is 100. Yeah. So how would you prove this?
First, replace the 0 with something is false.
Okay. Yeah. First, replace this one with false. But then,
precondition is false, then we can
no, but we can get it from the other rules. So first, you can replace this one with false, and you can prove that the entailment is correct, and you can actually do that. Then you want to apply the rule for assignment. So you have to actually replace that false with the result of your post condition where x is replaced with 1. So instead of false, you have to write 1 equals 100 in the precondition. That's how you do this. So you have to change your precondition to 1 equals 100, which is basically the same as false. And you keep your post condition as it is. And then you apply the rule for assignment.
Let's consider the post condition precondition false.
Yes.
We can't do the same thing.
Yeah, this is again the same idea. Well, here actually you have to change the precondition to true.
False implies true.
Yeah, because false implies true. Yeah. Look at this one. This is also interesting. So my program is just while true do skip. So it's a program that never ends. And both my precondition and post condition are true. How would you prove this?
We need to show the program never ends. How to show that?
No, well, from Cox's point of view, you just have a bunch of rules and you have to prove it using one of those rules. Of course, our intuition says that since this never ends, this program never ends, it doesn't matter what you have in the post condition. But what rule do you want to apply? You have to apply the while rule.
We can only apply while.
Yes. But if you look at the while rule, this is how the while rule looked like, right? So you get not B here, and B was the condition of the while. And here the condition of the while is true, so you get the false here. You see, that's the idea. You have to somehow apply the while rule so that you get false in your post condition. But you will not just get false, you will also get whatever invariant you had, but you can use true as your invariant so that you have true here, and then you have false and true here.
Oh.
And then again, you have to use the rule of consequence to make sure everything matches up. Okay, this one is basically very similar to the previous one, except that the post condition is true. Again, you do the same thing, you get false and true here. This is again another case of the precondition being false. So you just make sure your precondition is exactly in the format where you can apply the rule for assignment. And then you say, okay, if I can do it with this precondition, I can also do it with false. And yeah, we have a bunch of other examples as well.